We are live now.
Okay.
Yeah. We are live now.
Okay. Yeah. I don't have anything. I only have to. They say that bad network quality. Sometimes I get message.
No problem, sir.
Should I mute or something? No.
Fine, sir. It is okay. Now.
Oh, no problem.
Yeah. Good afternoon, sir.
Good afternoon. Good afternoon.
Yes, sir. Myself, Lucky Sekia. And
yes.
So good afternoon, everyone. Today is a unique day for us. We have two eminent scientists lecture today. First half also we had one with Professor Harsh Gupta, and now with us Professor Vijayamohanan Pillai. He is currently professor and chair in the chemistry in the in Indian Institute of Science, Education and Research, Tirupati. Earlier, he was also director of one of our sister labs, CSIR Sikri Pilani, and before that, he was working in NCL Pune. So we are very much thankful to you, sir, for accepting our request to deliver a talk in our CSIR Summer Research Training Program, which is being coordinated by our CSIR NESC Jorhat under the leadership of our director, Dr. G. Narahari Sastry. So without much delay, I once again welcome you and all the participants of this SRTP program for this today's afternoon talk by eminent scientists. And now I would like to request our senior most chief scientist, Dr. M.J. Bordoloi, to introduce Professor B.K. Pillai. Thank you.
Hello. Good afternoon to one and all. It gives me immense pleasure, and also I feel very privileged to introduce our honored guest, Professor Vijayamohanan Pillai, who is a leading electrochemist from India, and who, after receiving his PhD from Indian Institute of Science, Bangalore, worked in many areas of electrochemistry, electrochemical power sources, power electrochemical sensors, bioelectrochemistry, and he worked about 2 decades in National Chemical Laboratory, Pune. As Dr. Lucky Sekia told, he is at present working as a Dean R&D and Chair of Chemistry at SRTP Tirupati. He is an internationally renowned person. He has more than 260 publications, 27 patents in many innovations in electrochemistry and materials chemistry, and he guided more than 22 PhD students in materials electrochemistry. He developed highly sensitive nanostructured platinum electrocatalyst for CO oxidation and polymer electrolyte fuel cells using Nepean-based composite membranes with functionalized carbon nanotubes, graphenes, and his research interests include materials electrochemistry, functionalization of carbon nanotubes, graphene nanoribbons, and hybrid materials for fuel cells, supercapacitors, and rechargeable batteries. He got many honors. I will say few. He got MRSI medal Bangalore in 1996, CSIR bronze medal in 2004. He is a member of editorial board of Bulletin of Material Science 2005 to 2016. Electrolysis 2012 onwards, scientific reports 2015 onwards. He is a fellow of Indian Academy of Sciences since 2008 and in Indian National Science Academy in 2018. He has been an erudite visiting professor, PhD, thus Memorial 2011. Professor Gurumurthy Mangalam, Endowment Lecturer, Annamala University in 2012. Professor Ruinikanta Borua, Memorial Lecturer at Guwahati University in 2013. Professor Selikanis Chiranjeevi, Endowment Lecturer Award, Andhra University in 2015. ICT Avon Padma Shri, Zilius Sidhu, Distinguished Speaker Award 2016. Professor B. Tim Gowda, Endowment Lecturer 2015-16. Mangalore University, National Prize for Research on Energy Materials and Devices by JNCASR 2016, Professor T.L. Ramasar, Memorial Lecture ECS India 2016, MRSI ICSC Superconductivity and Material Science Award, Material Science Annual Prize 2016, Dr. K.T. Asario Memorial Award, OTAI 2017, ISCB Award of Excellence Chemical Sciences in 2019, and Silver Medal of CSIR in 2019, and many more. He has also visited many foreign countries, including United States of America, Germany, France, Finland, Japan, China, Australia, for giving many invited lectures on many topics in materials and electrochemistry and electrochemical energy storage. In addition to being director of CSIR SICRI, April 2012 to October 2018, he held the additional charge of director of CSIR NCL Pune from June 2015 to 2016. He has so many achievements. I will not tell everything because of time constraint. And now I invite Professor Vijayamohanan K. Pillai for his afternoon session lecture on nanotechnology and its impact on future materials. Sir, please, welcome you again.
Sure. Good afternoon, ladies and gentlemen. Thank you so much for the generous introduction. Of course, Rakesh made a small slip. CSIR SICRI is not SIRI. SIRI is in Pillai. CSIR SICRI is in a place near Madurai called Karikudi. So CSIR has got all these, wonderful laboratories in various parts of the country. I had the fortune of working in 2 CSIR laboratories. I spent my whole life in CSIR NCL at Pune, and I joined CSIR SICRI, Central Electrochemical Research Institute in Karikudi, 2012. But I had also been to Pillai, Central Electronics and Engineering Research Institute. Most of the CSIR laboratories I have visited from one locality to other locality. Some of them were doing pioneering work in area of energy. Some of them, because I was also a director of a chemical cluster. There are 7 laboratories who work together to have major programs. So CSIR is a wonderful place for implementing many innovative ideas, interdisciplinary ideas. Although each lab is a theme, there are many multidisciplinary projects. That's why it is a wonderful place where if you have ideas without any restrictions on disciplines, you should be able to use it as a big team. So I would like to thank Dr. Shekhar Mande, DGCSIR, and also Dr. Naveri Shastri, Director of Jorhat Lab, for giving an opportunity to address all of you. I have mentioned that I will be talking to you on nanotechnology and its impact on future materials. Of course, my slide is not moving. How do I move the next slide? Yes.
Sir, go to PPT and change it.
Yeah. Am I audible?
Yes, sir.
And also the slides are clear?
Yes, sir.
Okay, good. Very good. So, ladies and gentlemen, it's a great pleasure for me to address all of you in these difficult times. We are all passing through some bad time because the pandemic has affected all of us in various ways. But this is also an opportunity for us to look at it. Although we are scared because what is going to happen, we have no idea. But the vaccines are about to come. We need to be optimistic. So young people need to be optimistic because future is always bright, despite the temporary problems. Now, I would like to talk to you today about nanotechnology because nanotechnology is an umbrella technology. It gives you so much of benefit. There is no branch of science and technology where nanotechnology has not made a big impact. Look at for the case of COVID-19. We are fighting with schools on various platforms. Some side we want the pandemic to be stopped. Some side we want it to spread to be mitigated. We want to have diagnostics. We want to have the treatments. So again, nanotechnology has made so much of benefit. You can look at it from simplest mask onwards. These days, highly efficient masks are possible where 3-layer mask where the polymers are nano-engineered. The pore size is tweaked in such a way that bacillus will not go, bacillus will go through, but virus will be blocked. How do we create that? Once we understand the surfaces, how adsorption can be tailored in such a way that the coronavirus spikes can be used for specific adsorption. So please look at in fighting with the pandemic itself, nanotechnology provides you various opportunities. Some cases there are nano level functionalization. Take a small gold nanoparticle, functionalize with a chemical in engineering, chemistry, material science, computation, and all of them. All these convergence is very important for getting holistic solutions. I can tell you before talking about nanotechnology, 1 or 2 such examples, just recent examples. There was a paper 2 weeks back in electrochemistry communication. How do you detect virus alone with a cocktail of antibodies? Cocktail of antibodies, you generate it. You can also immobilize enzymes. This is something called bio-nano sensors. In a similar level, nano level immunity can be created by designing artificial systems, immune simulation and suppression. This is a paper which came in ACS Nano. So look at just one small area. We are all fighting with the pandemic. You can always have a nano level formulation to control social distancing. Suppose you imagine you can also take a small sample, quicker analysis can be done. If you sneeze, how long the contaminants can go. This can also be done by nano level formulation. So you can see micro heterogeneous materials. Similarly, there are wonderful nano composites which can be 3D printed to make not only the mask but also for ventilators. You can see. So just one area of pandemic itself, you will have various opportunities of application of nanotechnology. I'll go to the next slide. How do I go to the next slide?
Sir, you just go back to PPT and just.
My enter signal is not working.
But it is working, sir. We are able to see your next second slide also, nanotechnology in the time of pandemic, that thing.
Okay, now the next slide I want, I put enter. Yeah, so I think it is taking a little bit of time, maybe because of. So before talking about nanotechnology, I just wanted to tell one example. That is why I started with about the COVID-19. COVID-19, all of us are scared, but look at the opportunities. You can have a nano level carrier for a drug. You can do something called repurposing, nano medicines. You can also do chemical functionalization. In vaccine development itself, nanotechnology contributed significantly. There are nanostructured coatings which will remove the virus, kill the virus. So all this shows that there are various areas of nanotechnology helping us to fight with the pandemic. One example, if some of you are interested in this area, you can look at this ACS Nano paper in 2020, which just came recently. How do you use nanotechnology to create specific immunity level against COVID-19? But there are many people who are more knowledgeable about talking about this area. Since I am more like a chemist or a material scientist working on nanotechnology, today I'm going to talk to you about how do we use nanotechnology. First, since some of you are novice, what is nanotechnology? What type of materials we can create by nanotechnology? For example, let us look at what are materials. Materials are made out of atoms and molecules. Atoms and molecules we need to understand. How do we understand this nanomaterial? Nanomaterial is made out of atoms and molecules. By atom, molecule by molecule, you design a material. When you design this material in the laboratory, sometimes you can create superhuman qualities in the material. It's not a dead material. Material can have attributes like a human organism. What is special about human organism? we all have a brain, we think about it, we adapt to it. So mobility, adaptation, these are all attributes of materials, and attributes of human brain, living organisms. So while designing such materials in the laboratory, sometimes it is possible for us to introduce these type of functions. That is why we talk about such materials, advanced materials. It's not the old material. We are talking about use nanotechnology to generate some wonderful materials which are not existing in nature. We call them as metamaterials. You cannot show that this material is there. That is why we call metamaterials. Sometimes while making material, we can create attributes of human life, intelligence, intelligent materials. At the same time, look at the type of materials available. I'm not talking about these type of materials. You can have an aeroplane wings made out of Kevlar, a polymer which is stronger than steel. You can have a non-stick tawa where the coating is made out of Teflon. Teflon is a wonderful material with lowest frictional coefficient. You can have a bulletproof composite. Bullet will not go through it. It's very tough material. So all these materials are conventional. You can have a carbon fiber for the tennis racket or a badminton racket which will not break. Now, compared to all this, these are not really nanostructured materials. These are all composites. Sometimes you may see nano level structuring. However, I'm going to talk to you not on these type of materials. I'm going to talk about next generation materials. What is special about next generation materials? These materials will understand the nature, understand what is the environment, and these materials have got almost like, how do we think? Almost like a human type of attributes. We call them as intelligence. So the chemists, materials in the laboratory, physicists help us to understand the interactions, and actually almost all applications are in engineering. That's why you will see chemistry is important, physics is important, engineering is important. We will look at these materials not as one material. These materials, the application comes in connecting these materials to the world, real world. That means as time goes on, we'll have an ever-growing network of connected devices, IoT. Even in such cases, these materials are very important. And sometimes we'll use computational capacity from the cloud and insight from machine learning, all these to design intelligent materials. Look at the type of materials available. Wonderful materials. Right from the industrial revolution to the present digital revolution, materials play a key role in all aspects of our life. There are functional materials. Whenever you look at a microscope, there is always a lens. This is a material, needs to be polished. These days we look at atomic force microscope, scanning tunneling microscope where subatomic resolution, 0.01 Armstrong, you can see much below atoms. This comes because of materials. We call them as functional materials. Structural materials and functional materials. This was an earlier classification, no longer used now because every material has a structure, every material has some functions. There's no dead material at all. But chemistry-wise, we call these are organo-inorganic. Conventionally, people used to classify organic and inorganic. Now, no. Many materials are mixtures. You may have a 3 nanometer gold. On the gold, there is a small skin of thiol. That means an organic, thin organic material. Sometimes we look at a core shell material. You may have a Fe or thin a material of, let's say, 5 nanometer, 10 nanometer, but one skin, one atom thick platinum. So you have a big thin or iron with one atom thick platinum. Some cases it acts like it is a platinum. That means we are fooling nature. It will show the catalytic properties just like a platinum lump, but platinum is only one atom thick on the skin, again like a core shell material. Sometimes you have an inorganic core, outer organic core. Sometimes you will have a core of different type of materials, cadmium selenide, and at the outer side you will have cadmium selenide with sometimes sulfide. So these are all properties. That means you are at a stage where we can tweak these materials, artificially engineer these materials. And during this engineering process, sometimes you introduce intelligence, smart materials, intelligent material, designer materials. Some of these are composites. And one of the greatest things happened in the last decade is that we can also do the processing in such a way that you have a device ready in shortest time, 3D printing. Very, very disruptive innovation. All these materials can be printed into actual form, usable form. It can be done on metallic structures, on soft polymeric structures. And these days, we don't look at one material, we look at one lakh of materials together. We use machine learning, we call it as genome, material genome. All these are important. While designing these materials, we also keep future in mind. That means we would like to look at circular economy, materials being developed for sustainability, materials developed for the green processes. That means we don't look at next 1 year, 2 year, no. We want to look at next 50 years. These materials should not create any adverse impact on the environment. These materials should be completely recyclable. That means all the loops will be closed. Material will not create any bad effect on the environment. That's why we talk about materials designed for a circular economy. Materials with impact on energy calculated, impact on environment calculated. They must not create any damage to the environment for next 50 years, 100 years. And all this because of nanotechnology. Several fantastic materials have been created. Some of them are super strong materials, 100 times stronger than steel. Some of these materials are so light, lighter than you can think about spiral silk. Sometimes you can make it into various shapes. And in certain cases, we also understand the macroscopic properties of those materials. These materials will be extremely useful, not one material, a combination of materials. The properties can be tuned. So the unique aspects of nanotechnology is that you will be able to tune these materials. Let me go to the next slide. I think slide movement, I have a little difficulty, probably due to yes. So why do you want all these materials? The primary reason is that wherever there is a global challenge, you always can have a critical material identified with the application. What are the global challenges humanity faces? Energy is a very important challenge. Energy is a perennial problem. For a developing country like India, we need more and more energy because we aspire to become a superpower. You have a huge population. You want to give minimum requirement for the people, the exponential growth. That means our energy demand will double, triple. So there is an exponential demand for energy. At the same time, the quality of the energy is also very important. We want energy to be created without creating carbon dioxide in the environment. Carbon neutral technologies we want. Similarly, water, similarly, food, environment, our environment image is very poor. So if you want to solve all these global challenges, you can see certain critical materials are needed. All global challenges are somehow linked with certain materials. That is why materials is the key. Water, you want cheaper water, you want to have some membranes, dirty water, contaminated water, you want to make it potable, you need next generation of membranes. So nanotechnology is intimately linked with almost all these applications. Look at our country at large. We have around 1.37 billion people. It is going to become 1.6 billion in next 2030. So what is interesting is we have a plan to have a 5 trillion economy. Our Honorable Prime Minister has unveiled a plan to have a 5 trillion economy by 2023. At the same time, look at this, we have a lot of problems. Even now, big cities, forget about the pandemic. Pandemic has actually given us some certain advantage with respect to environmental possibility. If you go to Nepal or if you go to Himachal Pradesh, you can see so many glaciers. You can see the Himalayan peaks now, which were not seen earlier because the pollution has come down. You go to countries like China, the air quality has improved significantly. Even for India, the CO2 emission has considerably reduced. So these are all actually unintended benefits of the COVID-19. Even in Europe, many places, Ganges, the water has become clean because we are all locked down. Industries have been closed. CO2 is not coming out. CO2 emission has reduced considerably. So these are all unintended benefits of the COVID. But of course, 15 million people have been affected. The death rate, mortality is very high. So one side you can see now, at the same time from an environmental point of view, there is a benefit. So I wanted to show you all this image because although India is considered as one of those with a lot of aspirations to become a global leader, you go 50 kilometers from big cities, you will see our life is agrarian. How much energy per day per person uses? Very small, 1.1 to 2 kilowatt hour. So per capita energy consumption is still small. Although carbon dioxide emission, we are maybe third most polluting country. First China, then US, then India. So with respect to CO2 emission, we are one of the third most. But with respect to per capita energy consumption, we are very poor. That is why if India wants to develop, we need more and more energy. For example, vehicles. We have roughly 20 vehicles per 1,000 people. It is increasing slowly. So one side we have an ambition to grow. We want to become a stronger country, more developed country. So the growth ambitions needs to be balanced of energy we generate. We need energy, but that energy must be of premium quality, clean energy. So how do we generate clean energy? What type of materials are available for clean energy? This is what is important for us. You can look at big cities in India. This city, I'm sure most of you know, from the best you can identify which city is this. 24 million people on 2019. Now it is increased. City is growing vertically as well as horizontally. A large number of people come from other parts of the country. COVID we could not control in this city. Actually, they have done remarkably well because there is a slum in this country, one of the largest slum in the whole world. Fortunately, we are all worried about COVID spreading, but the city has done very well. They contained COVID in that particular Dharavi locality. Look at another city in our country. I'm sure most of you know this city. 29.6 million people on 2019. This city is fighting with two other cities in the world to become number one. This city is fighting with Beijing to become number one in pollution. This city was the worst polluted city few years back. Then we introduced CNG, we became number two. Still, there is a fight who will be number one. The population, this city is fighting with Tokyo in terms of number 1 or 2. Now we are number 2, but soon we may become number 1. By 2030, the city will have somewhere around 36 million people. Tokyo will have only 34 million. Now Tokyo is number 1, but there is a negative population growth rate. Look at the traffic. So these are all the problems which we face. And there are several such cities in our country. Look at another city where you still see a lot of polluting ambassador cars. And there is also equally polluting Machli market. You can look at the population, Bangalore, Chennai, Kolkata, Pune. Pune has a dubious distinction because this is the only city where two-wheelers are more than that of people. Urban Pune, we have 3.5 million vehicles, 3.5 million people, while the total vehicle population is 3.62 million. You can imagine now. So these are all the problems. There was a bridge only for two-wheeler. Now that is also chalked up. So look at these problems which the country faces. Can nanotechnology help us to solve these problems, at least partially? A city is called as a mega city if the population crosses 15 million. 15 million is a benchmark. Now, all these red dots are 15 million. Look at the global distribution of such mega cities. Apparently, India is full of such mega cities. Not even China, not even Africa. All these places, mega cities are distributed. And please remember, this is a picture from 2015. Now things are changed, but changed for worse, not for good. Look at the type of things we see. So much of pollution quality index. Due to pandemic, it has come down. But before the pandemic, before December, it was always poor. Look at if you look at the picture from outer satellite, India is so browny patch, almost like Africa. This browny patch is essentially coming because of CO2, SO2, greenhouse gases, nitrogen dioxide and sulfur dioxide gives you a green patch. This shows that our environmental quality index is very poor. How do we overcome? What is the best mechanism to get a cleaner environmental footprint? One way is that look at the energy management, energy generation, energy storage, and energy deployment. Transportation issues, how much energy we use, how much we generate. And this is also intimately linked with two things which globally human beings are not able to control. One is global warming, second one is emission of CO2. So temperature and the total amount of CO2 coming out, these two are all because of human-made activities, anthropogenic activities. This is the reason why all countries came together, made regulations in such a way that globally the carbon dioxide emission needs to be curtailed. India was a signatory. India committed that we will reduce carbon emission 25% by 2020. Because of the COVID, we are a little bit down, but we are sure that we will be able to make sure the global commitments which we made will be honored. So every country has promised that we will do everything possible to reduce global warming by 2 degrees or if possible 1.5 degrees. This happened during from Kyoto Protocol, and Kyoto Protocol is going to expire in 2020. United Nations Framework on Climate Conference on Climate Control. There are every year it happens. Unfortunately, some countries, although 190 countries signed in 2016, US came out. Then after US, Australia came out. But still we are hopeful because Europe is behind us, when China is strongly supporting. So hopefully at some stage wisdom will, especially after COVID, the international cooperation might become much more stronger. Last year we could not meet in Madrid. There were some issues. Even the Chile meeting could not happen, but we hope that things will go in a positive manner. As far as India is concerned, our Honorable Prime Minister made a commitment that we would make 175 gigawatt by 2022, 100 from solar, 60 from wind, 10 from small hydro. Actually, this target, we have exceeded this target. 100 solar and 60 wind. Wind and solar, India has done very well. Now in such a way that our renewable energy portfolio is more than 20%. 24/7 we provide power. Completely our country provides power to villages. So as a result of that, last year we changed the target. Instead of 175, now the new target is we want to make 450 gigawatt by 2030. Or maybe I think 2025 is a little high. No, why do we put all this? Because although some targets are unachievable, little strong targets, or they are very stiff, it is once you give such target, something will happen. The general people, the ethos will be positive. Many things happen in industries. For example, look at the mobility mission. We have a very strong electric mobility mission. 2019, 1.6 million electric vehicles were deployed globally. After 1.6 million, 80 to 90% had lithium-ion batteries. Still, we have issues, but please remember, without nanotechnology, this would not have been possible. Nanotechnology provided very new materials for lithium-ion batteries. Price has come down. I would spend a little time on that. So please remember that under this perspective, you can see nanotechnology has provided so many benefits in various areas: energy, environment, medicine, diagnosis, therapeutics. So nobody can dispute this. However, some of the industries think that nanotechnology is nanotechnology because the fundamental aspects are given more importance. So looking from the historical perspective, nanotechnology, the origin of nanotechnology can always clearly be traced back to a lecture by Richard P. Feynman in 1959. American Physical Society meeting is where he gave a lecture on there is plenty of room at the bottom. The word nano was not used, but he made a competition who will make the smallest engine, smallest motor. He provided some funds, provided a gift, and accordingly, this triggered so much of activity in many places. The word nanotechnology was first time used by a Japanese scientist, Norio Taniguchi, that is his picture here, a professor of Tokyo University. He is the one who first explicitly used the word nanotechnology. Then onward, there were several things. 1981, SCM was invented, and 1983, AFM. So please remember, although many nanomaterials were there earlier, we had no tools to look at nanomaterial. That is why the invention of STM and AFM was a major milestone in understanding nanotechnology. Of course, afterwards, we had so many things, 1990, writing with atoms, and all these are all the apostles of nanotechnology. Several proponents. Richard P. Feynman can be considered as the first person who provided stimulus for starting nanotechnology. Then we had Norio Taniguchi, and then we had Richard Smalley. Smalley was a proponent. Smalley put a lot of funds. US National Nanotechnology Initiative was started by Smalley. And then we have Ijima carbon nanotubes, Kagi Kroto from UK. And there are many other people, including the latest person called Eric Drexler. Drexler has a Nano Institute. So this is only the origin. So origin can be traced in 1959 lecture, available in PDF. You just type Richard P. Feynman, 1959 APS meeting, you will get this lecture where he was a profound person with a profound vision. He made a price for $1,000 for the smallest motor. Of course, some students from Caltech PhD students made such a motor, they got the prize, and now actually it's the other side. So much of hype happens by Eric Drexler. Drexler talks about engines of creation. Drexler oversimplifies nanotechnology. But what is the core? If you want to understand nanotechnology, you have to understand 2 or 3 important points. One is that nanotechnology is a technology where you go to such a smaller level. We understand atoms and molecules using quantum mechanics. We understand the bulk matter by using band structure, metal, semiconductor, insulator. In between, there is a region called mesoscopic region where atoms come together. When they form 3, 5, 10, 100, sometimes what happens, properties will be a function of size. Atoms and molecules, we understand the structure. Bulk material, size is not important. But in this region, size is very, very critical. So you make some size, properties will change with respect to size. That is very important. So in nanotechnology, ability to tailor composition and structure from nano to meso scale with a precise understanding is important. Similarly, there are several probes now. Last 10 years, we have been able to generate so much of instrumentation, wonderful instrument. You can see atoms, you can see electrons, where electrons are. You can manipulate atoms. You can take a DNA, put one adenine, cut it, put it in some other region. So we talk about sequencing genomes. We talk about molecular scissors, CRISPR-Cas9. So all these are possible because our understanding has gone to such a final level with an unprecedented spatial resolution, 0.05 Armstrong. Below that is very difficult. So STM, vertical and lateral resolution can be 0.05, 0.09. At the same time, imaging reactions. So the dynamics of chemical reactions can be imaged by using these tools. In parallel, advancement in computational modeling also reached such a finest level. You can compute length scales and time scales which we could not do 10 years ago. And now we also can handle large data sets together. Please remember that all this convergence created a revolution. When the nano was started, the word nano comes from Greek. Nano means dots. So you talk about 1 billionth dimension, kilo, just like kilo, mega, you talk about 10 power minus 9 meter. But that was the origin. But what happened is, once the understanding reached a level, we can manipulate atoms and molecules. Whatever we could do from Industrial Revolution till now, 100 years, all that can be done in 10 years. The exponential doubling of information, just like Moore's law says, number of transistors on a chip doubles every year. In a similar manner, our understanding goes exponentially. This is why people talk about there are people who talk about convergence, singularity university is an example. People talk about that all the knowledge what created during last 200 years can be created next 10 years, that can be created next 1 year, that can be created next 2 months. This is what is the exponential change we are talking about. So molecular manufacturing revolution created. Industrial revolution, what you could do in 100 years, you could do in 10 years. And never before has world faced such a tremendous opportunity. Nanotechnology, industrial revolution, now 3D printing, computational advancement, all this allows you to have generations of technologies. So nanotechnology is not one technology. It is an umbrella of technologies. And these technologies of manipulating matter at the atomic scale, going much more lower than atomic level, you can clearly see 4 generations. First is passive nanostructures, first generation. After Feynman, after Richard Smalley, we could make some nanomaterials, metal clusters, semiconductor quantum dots, band structure can be engineered, band gap engineering, aerosols, colloids, coatings. This is the first level of nanostructures, passive nanostructures. Up to 2000 people have developed. You can see wonderful nanomaterials. By 2000 onwards, people would make active nanostructures, where the contribution to medicine, nanomedicine, became more and important. Biological nanostructures, nanotechnology or nanomaterials made 2 big impact here. One is in bio, other one is in materials. That is why active nanostructures, nanoelectronics. You could make single molecule, single electron transistors. You could make large number of devices. We see nano electronics coming in a very strong way and nanomedicine also coming in a strong way. That is where the active nanostructures came into picture, 2000 to 2005, 2006. Then comes 3rd generation technologies, systems of nanotechnologies. You can make 3D networking of nanostructures, hierarchical structures, bio-inspired structures, where again you can see wonderful materials. Materials with intelligence, materials which can walk, materials which can move, with materials which can remember shape. That comes in the third system, third generation called systems nanotechnology. Now we are in molecular nanosystems, where you will see convergence due to artificial intelligence, convergence due to artificial, not only convergence due to big data analysis. They are able to handle big systems. Colony in Mars, people are thinking about, is an example of molecular nanosystems. Reusable rocket launchers. You can see applications in various domains. It all starts with atom level. We can talk about different type of materials, zero dimension. Just small, zero dimension is nothing, so we talk about quasi-zero dimension. You have 1,000 atoms put together, 1,000 atoms put together to form a platinum cluster. It is equivalent to a zero-dimensional material. Or you have some 2,000, 3,000 atoms put together in a semiconductor quantum dot. When you make them as one-dimensional system, like one-dimensional wires, tubes, in the laboratory, when you want to make nanostructures, you have two broad philosophies, bottoms up and top down. Bottoms up means you make atoms, stitch them and make a structure, nanostructure. Top down means you state a big material breakdown. For example, you can take graphite. Graphite is a material with sp2 hybridization, graphite between layers, but take a graphite rod, cut, make a small graphene cluster, make it as a graphene oxide, reduce it from graphene few layers, then it is a top-down approach. Bottoms up approach means build them, take benzochronolone, stitch them, make a two-dimensional polyphenylene type of system, dehydrogenate and make graphene. So same graphene can be made bottoms up or top down. It doesn't matter, but you can talk about 0D, 1D, 2D, 3D in nanotechnology. There are several examples. We will see one or two examples, but why are they getting unique properties? One reason is that they have spatial confinement. Just like COVID is putting all of us locked down in our house, we are behaving like a particle in a box. So this quantization gives unusual properties. Many examples. IBM in 1990 itself, they started writing with atoms. One atom, IBM, written by atoms of xenon or nickel substrate. And this was in 1990. Now 2010, 2020, we are able to make a lot of coral structures with molecules. So Richard Smalley was, I mentioned about a very important proponent of nanotechnology. He made to US government, he made a statement, just wait. 21st century is going to be incredible. We are about to be able to build things that work on the smallest possible length scale, atom by atom, molecule by molecule. These nano things will revolutionize industries and our lives. This profound statement was made by Richard Smalley, a Nobel laureate in 1999. He died due to a form of blood cancer. However, even after the detection, diagnosis of cancer, he used to go with his lab to argue with the US Congress, get more and more funds for nano research. One way to understand what is unique about nanotechnology is, nanotechnology, whenever you look at it, properties should not be same as that of bulk. That is number one. Number two, properties should scale up or down with size convergence. So some of you must have seen this movie called Honey, I Shrunk the Kids. You go through a machine, you come 2,000 times smaller. This is only scaling issue. So these children will move in a soup, the father is about to drink. It's a very interesting movie. But here there is no unusual effect, it's only size effect. You go through this machine, you become 2,000 smaller. That means your eyes, your specs, everything become 2,000 smaller. Nanotechnology is not like that. Nanotechnology, once you have this mesoscopic range, you get unusual properties. For example, melting point. I'm sure all of you know, gold ring. If I take this gold ring, cut it into two, what would happen? Property will not change. Of course, my wife may divorce me, but the melting point of the gold will be 1180. It will not change. But if I make this gold, cut it into 2 lakh times in such a way that I get only 5,000 atoms of gold, melting point will be different. Color will be different. For example, melting point of gold, you can see changes with size. 2 nanometer, 600, so 8 nanometer, 700. Once you get around 20-30 nanometer, bulk melting point, 1100. Same way semiconductors, you will see band gap keep on reducing. This is what we call as band gap engineering. So gold is a typical example because gold gives different colors with size. Many people have used gold. Even in Roman architecture, Roman cathedrals, they were using gold to make interesting color combinations, almost like a smart material. So gold, interesting aspect of gold is not only size, shape also controls the properties. It's a very well-known example. Somewhere around 2000, people have made gold of various sizes. You make a triangle, one color. You make a rod, another color. So size and shape dependent properties of gold is very well known. Michael Faraday is the one who observed it first time. He made gold colloids. His gold colloid is even now stable. 1800 he made it. If you go to London Museum, you can see the nanoparticles of gold created by Michael Faraday. Of course, those gold were protected by various starch molecules. He used also protective mechanism. That was different. Nowadays, we make gold and we also another semiconducting cadmium selenide. You can make it because these experimental demonstrations are very, very visible. Color and size, colors, a variety of colors can be prepared with the same material with the different sizes and different shape. For cadmium selenide, band gap is systematically changing. Gold nanoparticle color, optical color, we call it as a plasmon absorption, that keeps changing. So optical properties, electrical properties, interestingly, people were making such nanostructures even thousands of years back. Lycurgus cup is made out of a glass, but when you make the glass, you use silver and gold nanoparticles in a particular ratio. This cup used to be given to the king for drinking wine. This cup gives different colors. Transparent light, it gives you greenish color. In reflected light, it gives you reddish color. So why did this color difference came? Only because of the nanoparticles. Now, recently, people have investigated this. They have got a lot of evidence for this. So let me come from nanotechnology. How do we come into different types of materials? When you make these materials, you look at multiple functions. So gold cluster, you make a nano clusters of gold in the rod form, the various shaped prism, spherical particles, rod-like particles, wires. Then you may also need to give a protection by organic molecule. Sometimes this organic molecule may be electrochromic, thermochromic. So we'll have multiple functionalities coming into the material. It's not one material. We are talking about supramolecular system or a material created atom by atom, molecule by molecule. At that time, sometimes it is possible for us to introduce also properties like intelligence. We call them as super materials. Such intelligent material can be classified into passively intelligent, actively intelligent, and very smart or very intelligent. Passively smart systems, they know what is happening. They can understand and change, but they cannot store information. They don't have intrinsic fields. Actively smart materials, they have field, they have memory, they have trainability. They are much more, the degree of intelligence is much more for actively smart. And very smart systems, even something totally untoward happens, they can extrapolate and take a corrective action. That's why this is almost like a human brain. We call them as super materials. I can tell you several examples. In the next maybe 10 minutes, I would give you a few examples. Smart tennis rackets. Smart tennis racket knows what is in the mind of the player. If you want to go for a powerful smash, it has one shape, maximum power to the tennis ball. If you're going for to picking up a small drop, very gentle drop, you can control that. Shape changes. The streamlined motion is essential for drop, while when you want to give maximum power to orient action, that means the airflow, air viscosity, all that can be controlled by the shape. Similarly, smart cars, if you miss one installment, car will go to the factory. It will not come back unless you pay interest. Smart toilet is an example to show you really smart, actively smart, and very smart. When you are in the toilet, your body fluids are analyzed, you get a digital readout. For example, your urine contains 0.1% of albumin, there is a proteinuria, you may meet your doctor. This is coming from a passively smart system. With an actively smart toilet, information stored, compares. It says that last year you had albumin only 0.1, this time it is 10 times more. So you have some problem and it will do the diagnosis. Actively smart toilets will have biochips, several biochips. It tells you about all the systems, it stores information. If it is very smart, information can do, even totally untoward situation happens. Suppose you are in the toilet and you become unconscious. Information goes to your doctor that your patient number so-and-so is lying unconscious in toilet and go with an ambulance, take him. This is an example of a passively smart, actively smart, and very smart system. Now you can think about smart coatings, smart aeroplane wings, shape changes happen. So all these smart materials in a nanotechnology laboratory, when they design, they can create such attributes: self-diagnosis, self-tuning, self-sensitivity, shapeability, switchability, self-repair, selectivity. These are all the attributes. We can inculcate such attributes in this material while designing. Typical example is again from a movie called Terminator 2. I'm sure most of you would have seen this movie. We are not interested in the hero of the movie called Arnold Schwarzenegger. We are interested in the villain of the movie called T-1000, because the villain's body is made out of a smart material, an electro-rheological fluid. You apply electric field, viscosity can be controlled. So viscosity can have a non-linear change. You put this villain in a room, he can come to the keyhole, adjust viscosity, ooze out, and self-replicate, self-assembly. This is how nanotechnology has helped us to make such materials. If you put a bomb on the villain, he can explode into 2 lakh pieces, but within fraction of a second, he can come back and self-replicate. That means he is virtually indestructible. Several examples are there. I will not go to details. These are all examples of such materials called electro-rheological fluid. Electro means electrical, rheology means flow, viscosity control. Similarly, there are several color-changing materials: photochromic, electrochromic, thermochromic. They are all intelligent materials, and nanotechnology helps you to design. For example, you can make a color can be changed based on absorption, based on electric field. You can make an electrochromic cloth out of a conducting polymer. You apply 1 volt, it will be green. 2 volt, it will be blue. So based on how much electric field you apply, color can be tuned. And similarly, we look at nose, how a human nose functions. Biological organisms we study, because the more we look at biological organisms, the more we are amazed, because of millions of years of evolution, how nature has perfected the design. We look at human nose. Suppose you cut my nose, not my nose, your nose. There is an olfactory epithelium. There are at least 10 power 10 receptors. How these receptors are designed? We look at that and design artificial noses. So whether it is a human nose or a dog's nose, how the functioning happens, accordingly, now we make an array of the sensors and we can have artificial noses. So there are several such intelligent materials. I will not be able to cover several such materials, but there are electroceramic materials, lead zirconium titanate, PLEZT. We put lead, we dope it, accordingly we can control the curie temperature. We look at how a fish communicates with another fish, design hydrophones using lead zirconium titanate. Look at human nose, design smart sensors. How dolphins move, accordingly smart aeroplanes. So the major point I would like to talk to you is that bio-inspired design of materials, biomimetic chemistry. For example, look at spider silk. What a wonderful material. To touch it, very, very soft. Want to break it, very difficult to break. So there is no material which is as soft as spider silk to touch, at the same time very difficult to break. Strength is very high. Strength to break Newton per meter square. Look at spider silk, 1 into 10 power 9, while Kevlar, the one which is used for aeroplane wings, artificial polymer, 4 into 10 power 9. Rubber is 1,000 times weaker. Human tendon is also wonderful, like a spider's milk. So these biological materials, why did they get such unusual properties? Because of the structure. Spider silk structure is something which people have done a lot of work. What is called the beta cage structure. Composition wise, it is all soft material. Alanine, glycine, 95% alanine and glycine, very small percentage of calcium phosphate. But the way calcium phosphate is aligned, the orientation, that is almost like a 2D material. That's why there's a pillaring of 2D sheets. That is what gives you unusual tenacity for spider silk. 5 times as strong as steel, structures 30% before break. So these are all examples where how does nanomaterial contribute to design unusual materials. We look at spider silk and make it in the laboratory. Maybe energy is one example where I can also suggest 2-3 examples. Energy, because we are all badly in need of energy. We want carbon neutral energy generation technologies. And nanotechnology has made a profound impact on this. Battery materials, lithium batteries, sodium batteries, solar, photovoltaic coatings, dye-sensitive SLR cells, electrocatalysts which can replace platinum, non-metal free electrocatalysts, water electrolysis, hydrogen energy generation, fuel cells, redox flow batteries. So you can see now energy is where you have several, you want one side megawatt to milliwatt for a small wearable devices. So right from cardiac pacemakers to megawatt level of energy generation by nuclear reactors, nanotechnology has contributed significantly. I will not go to details. Most of the automobile manufacturers, they know how to make a green car. It's not the color, but it has zero emission because of nanotechnology. Wonderful materials. Electrochemical power source is an area where nanotechnology has provided immense contributions in terms of materials, in terms of structures, in terms of devices, batteries, fuel cells, and supercapacitors. Because I work in this area, I make different type of materials. Take a fuel cell, for example, polymer electrolyte fuel cell. Polymer electrolyte fuel cell takes hydrogen and oxygen and generates electricity. No CO2 at all. So CO2 neutral. And you can always generate hydrogen from renewable resources, solar or wind. So carbon impact is not there at all. But look at what nanotechnology has done. Every component in this, carbon-based composite, graphene-based composites, the nanostructured polymers, platinum replaced by small nanoparticles of carbon. So you can see every component here, nanotechnology has generated something very interesting. Intelligent materials, intelligent electrocatalysts. Lithium battery is another example. 10 years ago, lithium battery was very costly, $2,000 per kilowatt hour. Now look at the cost, almost 100. How did it happen? Performance has improved dramatically. Of course, scale has also helped, but more than that, materials evolution. 1991, when Sony commercialized this, there was only one material or two material, lithium cobalt. Now, no, you have plenty of materials. Even electric vehicle people have a difficulty to choose which material. Some people use LFP, lithium iron phosphate, sometimes manganese, sometimes cobalt. You can see now. So materials revolution has propelled electric vehicle technology. Cathode, anode, new electrolyte, new separators, a separator which knows that the battery is going to explode. Smart separators, intelligent separators. Before the battery shorting, separator stops. A paper in Nano Letters 2016 and the paper in Nature Communication 2014 both says that lithium dentate can be stopped by the separator. So separator knows that battery is going to explode and separator stops the battery. No wonder that last year Nobel Prize went to lithium-ion batteries. A team of 3 people, 97-year-old, 97, mind you, so such an old age. We don't even think that we will live up to that age. So 97-year-old, now he is 98. John B. Goodenough, who was a physicist, something called a 72-year-old mechanical engineer called Akiro Yoshina, and 77-year-old, 78-year-old Stanley Whittingham. So look at this team of 3 people. They have created material revolution. One mechanical engineer worked 16 years in one company, only looked at different forms of carbon, how to commercialize. One chemist working only on intercalation for several years, again in one company only, and one academician, Professor John B. Goodenough, a condensed matter physicist. So the team itself is unusual. That is the reason why we have nanotechnology has generated so many materials in this area. In fact, the first book written by computer, scientific book, is lithium-ion batteries, a book written by machine intelligence. This is the first of its kind. Because this book needs expertise from mechanical engineers, chemical engineers, electrical engineers, chemists, physicists, material scientists, and it's impossible for one person to look at it. That is why this is an example of such an interesting confluence. So maybe another 5 minutes I would like to wind up. What are the applications? There are plenty of applications for nanotechnology. Anywhere you look at it, I started with COVID-19. You can see treatment, diagnosis, so medicine, engineering. There is no branch of engineering where nanotechnology has given a profound application. Automotive industry, chemical industry, nano-level paints, cricketers use nano TiO2 to protect you from UV radiation, beer protection, mask making, medicines, drug delivery system. Earlier used even injection, the drug goes everywhere. If you have a small tumor in a small region, why should you contaminate the entire body by their drug? That is where smart drug delivery systems are important. Polymer drug is covered in a polymer. Polymer goes to the site where there is either enzyme or there is a pH change. The polymer opens, oozes out the drug, and then polymer closes. So this is what is called drug delivery system. Similarly, medical rapid test, processes and implant. All these are areas of nanotechnology. And they have got wonderful materials. Graphene, for example, a two-dimensional material, one layer of carbon, sp2 hybridized carbon, where electron can move in this layer with a relativistic speed. 1/100th of the velocity of light, and this electron motion is called ballistic transport, because resistance doesn't matter, impurities will not matter. Every time this electron moves with such a speed that mobility is unusually high, we call it as Dirac fermions. There is no resistance at all. And what will you get? You will get devices with 1000 times better efficiency, much more faster. I will not go to details unless somebody is physically interested. Graphene is one example, but there are plenty of such 2D materials. Insulating material called hexagonal boron nitride, semi-metals called silicon, germanium, tin. You can have metallic structures, VO2, TiS2. You can have band gap adjustable materials, molybdenum sulfide, tungsten selenide, what is called transmetal dichalcogenates, because valence band and conduction band. If you look at the valence band, there is a small strong spin-orbit coupling. So you will see unusual properties due to 2D materials. We call it as ballistic transport. Again, I will not go to details. 2D materials have created so much of excitement in the last 5 years. I work in one such material called phosphorine. Graphene I used to work earlier, now phosphorine. Phosphorine is also 2D material. Phosphorine is a material whose band gap can be controlled very easily. Take black phosphorus, apply electric field, make quantum dots of phosphorine. 6 nanometer, 5 nanometer, 3 nanometer, 1 layer, 2 layer, 3 layer. These are all interesting 2D materials. And some of these are important to make intelligent coating. Intelligent coating means coating knows what is happening in the environment, and coating can sometimes self-healing coating, corrosion protection. There is so much work using intelligent coatings. You can protect a corrosion, you can put a corrosion inhibitor inside the polymer. Polymer knows that there is a crack, polymer opens and oozes out. These type of intelligent coatings are there. Conducting polymers are used. Sometimes you use mercaptobenzothiazole. It's a corrosion inhibitor that is stuck in this polymer. Polymer opens. Similarly, when you apply stress, so the external forces, we call it as stimuli responding material. Stimuli can be pH, ionic strength, temperature, pressure, surface tension, light. You can tune the material in the laboratory based on the composition. In a similar manner, these days you have systems available, smart systems. Thermoelectric generator, you have a small watch or you have a ring which tells you about the human health. So you can design such biochips. Biochips means essentially enzyme immobilized, either enzyme immobilized or sometimes microbial devices which can give unparalleled information about your health. So we use advanced materials, we use flexible fabrication technologies and sophisticated computational platform. For example, some of them, they also have bad effect. When carbon nanotube was invented, some people reported that it can have an anti-aging effect. So people made several creams of carbon nanotubes coated to become beautiful. But after 10 years, they found that it developed skin cancer. So the company called Botox anti-aging cream was taken away from market. So this is one example of a very interesting application. Similarly, these days you make wireless ECG shirts powered by hybrid thermoelectric device. So you can also connect it to photovoltaic cells. Now, so I have just talked to you about nanotechnology's benefits, different type of materials. You must also be aware of what is called anti-nanotechnology. There are people who are against nanotechnology. They come and say that, look, nanotechnology has not really changed anything. There's too much of hype. Nano level of material, there is a lot of toxicity. They will go in the human body and sometimes they affect your kidney, nanomaterials will accumulate in your liver. So these are all not right. There are some toxicity issues, especially for medicinal applications, but there are well-defined standard protocols, especially by the European community about nanotechnology. So potential risk of any new nanomaterial you find, you need to evaluate the potential risk of this material, environmental exposure. You have an engineered nanomaterial, what will be the impact, cytotoxicity, all that, there are methods of evaluation. So let me just summarize. I've been talking about nanomaterials. How do you use nanotechnology to make materials of the future? Future is something which nobody can predict, but there are directions. For example, there are very clear examples of voice-driven furnitures, voice-driven shoes. You can always call come and shoe will come, because voice can be identified by the furniture. Voice control chips are available. So this is where applications of all these nanomaterials have been integrated layer by layer. You can have a cloth with a part of it as a power source. Battery can be generated for your mobile. When the mobile charging is on, you can connect it on your shirt. These type of wearable devices, wearable power sources are available. Flexible, bendable power sources. Similarly, CRISPR-Cas tells you about defective gene replacement. These days, it is also possible to have reconfigurable coatings and reconfigurable composites. So 2030, many of these applications will converge. People talk about even human brain enhancement, augmentation by various devices, possible thought recognition, emotional control chips. So these are all some of the futuristic aspects where advancement in material coupled with computational capabilities will give you several applications, ending with Mars-based villages. I'm sure Elon Musk. Now there are 3 space programs in this month, one by UAE, one by US, and one by Japan. So I'm sure that people like there are several private players in this space. Space is where all these applications and nanomaterials will converge. Eventually having a colony in Mars or some other extraplanetary scale. Biology is another area where you will see a lot of transgenic animals by CRISPR-Cas9, not a robo-roach, robo-mouse. All this will happen. Of course, ethically there are questions whether when you control human brain by such artificial implants or by applying electrodes, is it right or not? Because the question of moral, immoral or amoral, that question can be manipulated by our understanding of human brain. So human brain, again, nanotechnology has contributed so much that the synapses, although single neuron imaging has not happened, we understand how the neuron joins another neuron at the synapses, sodium ion, potassium ion concentration changes, the action potential is generated. Again, nano level devices are available for augmenting human capabilities, cochlear implants, retinal implants, in a similar manner, memory chips, even there is deep brain stimulation. So let me just summarize. I started talking about materials, how India as a growing country, what are our energy requirements? Large amount of energy is needed. Energy availability is a perennial problem for a country like India. Our demand for energy is exponentially growing. At the same time, we have a very poor environmental quality index, much lower than even that of China. How do we improve the situation? One way is that we need to dramatically change our energy management policies. Of course, there is a high level of planning by NITI Aayog to re-engineer all the energy plants. We need to generate more and more renewable energy. We have done impressively well in the area of solar and wind, but storage is an area we have not done much. We don't have even a single lithium battery manufacturing plant in the country, although we use billions of such devices, all mobiles, all laptops. Manufacturing is not there, and we talk about mobility mission, very huge program where by 2030 every vehicle manufactured in the country must be electric. But where are we going for batteries? We need to depend on outside sources. Although indigenous technology is available here and there, but they are not mature. Private companies do not have the confidence to invest. So these are all different level of policy issues. But no doubt that nanotechnology has made a big impact on the way we live. Devices have become smaller, faster, smarter. Coupled with artificial intelligence and mega data, there will be a much more profound change in our life. Just like the pandemic has created so much of disruptive lifestyle to us, like these conferences, meetings, all that, you will see an increasing trend. One area is smarter batteries, smarter supercapacitors, intelligent coatings, infrastructures, health. Health is something where you will see profound change by nanotechnology. Maybe life can be added, whatever is the mortality rate will come down. And when you are 70 or 80, you go and do a re-engineering of the entire body, tissue, everything, brain, liver, heart, everything. So this is also something which you can think about application of nanotechnology, and you can combine like a newly refurbished vehicle in a similar manner. Everything is corrected. Of course, I spoke about nanomaterials. Many of these materials are in the laboratory. They are still in lab curiosity. Nano rooms are available now, coupling nanomaterials to make rooms. Some of these are very expensive. There are also security and privacy issues, moral issues. For example, these days you get a aura is a ring. Aura ring, you put it on the finger. Arterial pressure, BP, glucose, everything is monitored. Aura ring gives you 250 measurements per second, compared to Fitbit, which is only 12 per second. So there are 3 sensors on that. So this will give you diagnostic about your health every moment, and you can connect with a mobile. Similar manner about the brain. If you have your central nerve system has any difficulties, you can always look at with a laptop, with a mobile interfacing is available. So in summary, nanotechnology, if you want to understand, use it for designing future materials. What we are trying is a philosophy of creating a higher dimensional materials structures by providing life functions of sensing, actuating, and control. These days we also have 4-dimensional materials. 0-dimensional I talked about quasi, 1-dimensional, 2-dimensional, and 3-dimensional material, and 4-dimensional. So all these materials will change our lifestyle in the next 20 years in an unimaginable way. With this, let me thank all CSIR once again for giving me an opportunity to talk about the wonderful world of intelligent materials created by nanotechnology. Please remember that basics, chemistry, physics, and biology are very important to design such nanomaterial, including mathematics. So if you go for an MTech in nanotechnology, BTech in nanotechnology, etc., no, we need to understand physics, quantum mechanics, then only the actual power of nanotechnology will be visible. With this, I hope you have understood the essence of nanotechnology in material science. I would like to thank Dr. Narendra Shastri and Dr. Shagar Mande for inviting me. And if you have any questions, I will be happy to answer. Please use the chat box, because sometimes it's very difficult to answer one-to-one in a virtual platform. With this, thank you all.
Yeah, thank you very much, sir. Thanks a lot from our side, and on behalf of our director, Dr. G.N. Sastry, and the whole team of SRTP, we must thank you for your wonderful thoughts.
Yeah, shall I unshare so that...
Sir, you can unshare the slides.
Because I can't see the chat box otherwise.
Yeah, sir, actually, this session is live in YouTube as well as Facebook also, in addition to MS Team. And there are more than 1,000 of participants, and a lot of questions we are getting, not only in MS Team, also in YouTube and Facebook. So, sir, it was really a wonderful talk, starting from the basics of nanotechnology to its application in different sectors like lithium-ion batteries, and then in nanotechnology in medicine.
Shall I unshare?
Sir, our student will ask actually selected questions, because there are many questions. So I request Lisa Moni to ask the questions. Yeah.
Okay, I am not able to see the chat box. Yeah, please ask.
Thank you, sir. On behalf of our director and all the SRTP team members, we thank you, sir, for your insightful presentation. It was indeed a great pleasure for all of us to listen to you. Your lecture was really very interesting and informative, and we could not agree more on how nicely you have highlighted all the significant areas. And I'm sure most of us were unaware about the future impact of nanomaterials, and we are grateful to you for giving us an insight. No wonder, sir, all the live platforms are filled with appreciation remarks, and some of them have even gone on to say how this was the best lecture on nanobasics they have heard. And so there are numerous questions, sir. We have selected few of them. So if you permit, I would like to go forward.
Yeah, so 2 things. I do not know how much time you have, but I also encourage all of them. You can give my email ID. Okay.
Yes, sir.
I would like to satisfy all the questioners. Please tell that due to any reason, if we are not able to provide answer now due to time restrictions, I will be happy to send it to them by email. Okay.
Okay.
And then based on your time, you can always ask me selected questions. No issue.
Yes, sir.
I am available.
Yes, sir. Okay, sir. Thank you, sir. Sir, the first question. is from Haripriya. She is asking,
Yes.
which type of nanomaterials, when used, do not cause any damage to the environment? Sir,
Let me
is that
rephrase. Yeah.
Yes,
Which type of nanomaterial?
nanomaterials? Yes. When used,
In use will not
cause
create
any damage to the environment.
Okay, see, there are several biomaterials, for example, polylactic acid. They are biodegradable. They do not give, if you nano engineer them, they will not give any effect to the environment. Now, when you say effect to the environment, you also have to look at the system, human system, cytotoxic. Many nano level medicines are there which are not cytotoxic. So unless the Haripriya, right, unless the specific application is mentioned, I will not be able to tell that what would be the impact on the environment. Suppose carbon dioxide is reduced. CO2 reduction is an important environmental problem. If I reduce CO2 to, let us say, methanol or ethanol, I use a catalyst. Catalyst is not going to the environment. Catalyst is a recyclable process. So any of these CO2 reduction or any of the nano level catalysts we use industry, they are not creating any adverse impact on the environment because they are recycled. Fuel cell. Fuel cell is an area where we use platinum, but the platinum can be recycled so that it doesn't give. Now you can say that platinum is obtained from a mine. At that time, mining has created an environmental impact. So these are all questions. Or even talk about electricity generation, coal. These are all the energy generation using technologies which emits carbon dioxide. So we call it as carbon positive, which is bad for environment, global warming, etc. Carbon neutral means we don't generate CO2, we don't also take CO2 in. So for example, solar and wind are renewable energy where energy is generated without creating any carbon dioxide. If you consider CO2 capture, CO2 reduction generation, for example, you can always have a lithium carbon dioxide battery. CO2 is used. CO2 is as an input. Now, so every time you generate 1 kilowatt hour, some CO2 is absorbed, like photosynthesis. These are all carbon negative. So carbon negative is going to be more and more useful for the future. Carbon neutral is already there. Fuel cell is a carbon neutral energy generation technology. I hope that is clear.
Okay, thank you so much, sir. So there is a common question, sir.
One more clarification. Lithium battery. Suppose you have an electric car. Electric car, if lithium battery is charged by solar or wind, then it is a carbon neutral. Otherwise, electricity, how you generate is important. So electric car does not automatically say that you don't have any emission. That is a misconception. Electric car is good where the electricity used for charging the battery is coming from a carbon neutral source. Okay, go ahead.
Okay, sir, there is a common question. So most of them has asked about the sustainability of nanomaterials.
Yes, yeah, it is a concern because many nanomaterials are not very stable. The moment you generate nanomaterial, since they have very high reactivity and high surface energy, they try to agglomerate. They try to come together. In certain media, agglomeration tendency can be offset by protection, capping. For example, you make 3 nanometer gold. 3 nanometer gold eventually will become 5, 10, 20. But 3 nanometer gold is protected by a thiol monolayer, then it will be stable for several weeks. Similarly, many nano level catalyst of 3, 4, 5 nanometer, you have to have a strong matrix where it is embedded. Matrix will prevent its agglomeration. So the question is very genuine. Many nanomaterials, when you prepare, they will be generated in nano, but post-wall ripening and many other agglomeration tendencies will make them unstable. So based on the type of applications, some of these could be protected. Sustainability of nanomaterial is always a question. Some nanomaterials can be stable for 1 month, 2 months, 3 months. Carbon nanotube, if you make it, they are stable for several months. So if platinum, gold, nano catalyst, if you make it in very small dimensions, unless you take extra level of protection, for devices you can do encapsulation, solar cells and such cases. So the sustainability answer, how do we make nanomaterial sustainable, depends intimately on the type of material and the type of environment and application. Okay. If they have more specific nanomaterial sustainability, please ask them to contact me by email. I will be happy to answer.
Sure, sir. Sir, so there is the next question is from Meenakshi Savankar. She is asking how to use nanotechnology in agriculture for slow release of fertilizer.
Yeah. So, nanotechnology, one of the areas where nanotechnology has made big impact is in agriculture. Something called root engineering. So the fertilizer, if excess fertilizer is there in the soil, it is not good at all. It is bad. So normally, what people use is an NPK sensor or a sensor to detect the level of agriculture micronutrients present in the immediate vicinity, and use this feedback mechanism to provide this. So you can have an adsorption layer where nanomaterials are adsorbed, micronutrients are adsorbed, stored there and released slowly. Now, how do we release them? Release them based on intelligent coating. Intelligent coating can be a pH dependent process. So looking at the soil conditions in a system where you can artificially design a precision agriculture system where intelligent materials are used to store these agricultural micronutrients, release them when there is a need. For example, potash. How much is the potash content in a particular zone? Once you detect if it is lower, you can use this feedback to release them. So there are several adsorptive materials, zinc oxide. They can absorb these micronutrients. I hope that will give a clear answer to the question. In agriculture, we need such nanomaterials.
Thank you, sir. The next question is from Ranjini Tyagi. So he's asking, are photofabricated nanoparticles more effective for treatment of any viral diseases?
So can you just repeat the first part?
Sir, are photofabricated nanoparticles more effective for treatment of any viral disease?
Yeah, let us talk about photofabrication is something which she has used. See, suppose you are using UV. UV itself kills some viruses and bacteria, right? So photofabrication, fabrication is using photolithography you are using. Imagine you use UV radiation or electron beam to make a structure. The structure doesn't store light. So photofabrication per se will not be able to kill bacteria or virus. What is there in the structure? You can make a photofabrication usually is helping fabrication, thin layer structures. But if you are directly using, let us say, something which can emit light, UV emitting, they can be more effective. Fabrication per se doesn't give anything. What is there after fabrication? What are you using in that? That gives you the antiviral or antibacterial properties. Okay?
Okay, sir.
So the answer is no. Answer is no.
Sir, the next question is from Vaidehi Shripad. She's asking, can we use nanomaterial for bioremediation purpose?
Yes, very important, very good question. Because bioremediation is conversion of waste material into energy. These days, people talk about microbial fuel cells. Microbial fuel cells need nano-level catalyst. Sometimes you immobilize an enzyme. Enzyme will convert all the waste materials coming into useful materials and generate energy. Bioremediation also means converting, let's say, toxic materials to the environment into useful form. So I think that question is very relevant. There are many important nanomaterials. Nanomaterials sometimes along with light. The previous question you imagine, photo. So photoelectrochemical remediation is also possible where you have nano level materials. In addition to that, you use also light to transform the toxic materials into useful materials. That is what is important. Bioremediation, photoremediation, electroremediation, they are all important technologies.
So the next question is from Dipti Bhaskar. She is asking which approach, that is top-down or bottom-up approach, is most preferred in the field of nanomedicine?
Yeah, I may have to think about it because nanomedicine, if you talk about it, whether tops down or bottoms up. In nanomedicine, sometimes very difficult to try a top-down approach because medicines are created in a laboratory in an atomic level, molecular level. It's not like a graphite breaking into a smaller piece. Okay, that is why obviously in nano formulation in pharmaceutical industries, always you start with atoms and molecules. That means bottoms up approach is much more useful than top down approach. Top down approach is important only when you want to make, imagine you want to make a graphene or you want to make some gold, such cases. So formulation is better to use molecular synthetic routes. Okay.
Sir, if you have time, can I ask two or three more questions?
I have plenty of time. You can ask 100 questions also, no issue. Okay, I'm at home and due to COVID, no problem. Please go ahead.
Okay, sir. Sir, Kedar Padia wants to know, how do regenerative materials work?
Yeah, regenerative materials, right?
Yes, sir. Yes, sir.
Yeah. So it is not very clear what do you mean by regenerative. Is it recycling? I can consider it as recycling. See, there are tissues which can be regenerative. So in the area of nanomedicine, if he is, whether he is talking about that, I am not very clear. If he is talking about regenerative tissues, they are all soft polymers, polymer scaffoldings. So once some encrustation happens, the encrusted material can be removed and then the regeneration can happen. Regeneration can be externally triggered. If that is a question he asked. If it is recycling, it's entirely different, like lithium batteries or battery recycling. So if it is a regenerative material, most of these regenerative materials are composites, layer by layer. If there are certain, say, some amides linkages created, they will do hydrolysis and the structure is generated. So there is a material loop formed, and as a result of the reaction, the new material is again and again forming. That is how regeneration happens. Now, if it is specific tissue, then we need to look at the biological structure. Okay.
Sir, there is a question from Sneha. She is asking if our ancient literature has any evidence of nanotechnology.
Yes, it's a very well known. Many of our basmas, okay, they had small amount of gold, platinum, mercury. All these were extremely small. There are projects running on looking at Ayurvedic compositions. What was the nano level of metal content in that? So they were all, in Charaka Samkrita and all that, many medicines and formulations were there. Some of the structures were obviously nano, just like if Faraday made nanoparticles of gold. We didn't have enough tools. So there is ample evidence to prove that in ancient literature, especially in Sanskrit, there were many nanomaterials being utilized. Look at iron pillar in Delhi. Iron pillar was known as no corrosion at all. Why iron pillar doesn't corrode? Russians came almost 20 years back, took a small sample. They found that there is a small carbon nanotube structure in this. So the iron, which is, there are several theories. Some people say these people did a lot of puja on this. Used oil formed after burning, forming carbon, got incorporated. But India was very strong in alchemy. Not only alchemy, metallurgy. Damascus sword again is coming from India. Okay. So you imagine metallurgy, Indians were very strong. Many of these had nanostructures. At hindsight, when we do analysis now, there is enough experimental evidence that many of these had unique way of making involved nanostructures. So her question is very relevant, very important.
Thank you, sir. Sir, there are actually hundreds of questions, so we will just ask you now one last question.
Yeah, you can ask one last question. Yeah, you can forward all that to me by email, maybe not tomorrow, but before this Sunday, I will try to answer as much as possible, maybe even all. Okay, no issue. Yeah, that's why I told you. I gave you the freedom based on your time. You plan and ask questions. All others, I would make sure that everybody gets a satisfactory answer by email.
Yes.
Yeah.
Yes, sir. Sir, the last question that is from Rishabh Gupta. He's asking what will be the best suited nanomaterials that can be used for preparation of drug delivery systems?
What would be the base material or?
Base suited nanomaterials.
Sorry?
Okay. Sir, what will be the best suited nanomaterials, suitable nanomaterials for preparation of drug delivery?
See, my answer to his question is that he is using drug delivery, so we can't use any toxic material. Okay, there should be cytotoxicity. So we need to look at very small polymer structures with some amount of amide linkages, which can be hydrolyzed once it goes to the site where the drug is to be released. So there are many polylactic acid, there are several types of polymeric structures used for even prosthesis, implants. Such polymeric structures can be used as a drug carrier. So controlled drug delivery, many people have used different type of polymers. Exact structure can be available. I don't work in polymer area. I cannot tell him which material, but if he is interested, I can send him references. We see CLRA, for example, CLRA does work on controlled drug delivery. IACT, so our chemistry clusters in many CSIR laboratories, they are able to come up with new polymeric structures which will release the drug. I would tell him to look at NCL work, IACT and CLRA. These are the three labs where I am aware that work in this direction is going on. Even CCMB work is going on in this area. Okay?
Sir, actually, I want to ask you one last question for nanoscience background students like me. Sir,
yes,
what
please.
are the potential? Yes, sir. What are the potential upcoming 2D materials beyond graphene? Could you please highlight?
Yeah, I would say that you want the potential for research or for industry?
Sir, for research applications.
Yeah, research application, graphene, so much of work happened. Okay, last I would say that maybe around 5 to 10 years. So much of work, graphene oxide, reduced graphene oxide, etc. After graphene, we had seen plenty of work on transition metal dichalcogenides. Molybdenum sulfide, molybdenum selenide, tungsten sulfide, tungsten selenide. So what we call it as TMS, transition metal dichalcogenides. After these two, the systems came up like phosphorine, borofene, stannine, antimony. So these are systems where so much of potential exists because not many people are found methods to make them and to apply them. For example, that band gap engineering. Black phosphorus band gap is 0.2 eV. One monolayer of phosphorine band gap is 1 EV. So band gap can be tuned in a similar manner. Synthesis from black phosphorus by exfoliation, by applying electric field, by using microwave. The techniques to make these phosphorin are just coming up. Last few years it has come up, but they are light emitting. Whether you make 3 nanometer or 5 nanometer, accordingly the light emission changes. Okay, so 2D materials, lot of 2D materials are coming up now. Phosphorin is very important. Borofene is important. Antimony, stannine, bismuthine, people are not even made them. Maybe isolated 1 or 2 reports. I can only say that many of these cases, optical properties, there is also what we call it as electronic properties, nanostructure, nanoelectronics. Sometimes you will see them strain, changing the band gap. Electrocatalysis, nitrogen doped graphene can replace platinum. Phosphorine doped graphene can replace rhodium, oxygen reduction. So there are many cases where 2D materials are going to be important because noble metal can be replaced by 2D materials, metal-free catalyst. Okay. Hello.
Hello, sir. Thank you so much for patiently answering all the questions. Thank you so much, sir. Now I am handing over the session to Lakisakya, sir.
Okay.
Yeah, thank you so much, sir, for your illuminating talk and the question answer sessions. And actually, we are getting so much of questions as well as appreciative messages of your talks. That it's really wonderful. And our students, this Lisha Mani, Monty, and Rajiv, actually they have compiled a slide and it is being displayed in the screen now. So your talk, they have made some points and put it in a single slide.
Very good.
You can see that. Yeah.
I am so very, very laudable. My compliments to them because very well they have done it. And how many participants were there?
Sir, actually in MS team it was more than 550. And YouTube also it was 430, and Facebook also it was many participants. So maybe around 1,000. Yeah.
Okay, please send all the questions and I will try to answer it in next 1 week. Okay.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Actually, there are a lot of questions are there also. So we'll try to send all those questions to you by mail.
Because this is a popular topic, you know, agriculture to biology to nanomedicine to engineering. Yes.
Yes, exactly, sir. Exactly, sir. Yeah, exactly. So thanks a lot. And now I would like to request Dr. Manos Das to offer formal, vote of thanks. What Manos?
Yes.
Thank you, sir. On behalf of Director V. Norahari Sastry and our CSIR SRTP team, it's my great honor and privilege to offer my vote of thanks. So first and foremost, I'd like to offer my sincere thanks to you for your valuable and it's a very fruitful lecture for nanoscience and nanotechnology. It's a very general lecture that covering from the historical aspect of the nanoscience and nanotechnology to the modern nanoscience and nanotechnology. And it's a very fruitful lecture because it's highlighted the tremendous potential applications of the nanomaterial in the different area of energy, environment, medicine, biosensor, etc. It's a very helpful for our attendees, all the students of the BSc bachelor degree and master degree, also the mentors of the different backgrounds. So it will be very fruitful lecture for this Eminent Scientist lecture series. I also offer my sincere thanks to GN Norahari Sastry sir for their encouragement and guidance for smooth running of this SRTP, CSIR SRTP program. And also I offer my sincere thanks to all the participants, including students, mentor, and all the members of the CSIR SRTP teams. So thank you all. Thank you for this Eminent Scientist lecture series. Thank you, sir. Thank you very much.
Okay.
Yeah. Thanks a lot. Actually, Director sir is busy in that meeting.
No, I know. See, he called me that there's a director's conference. I know that. Don't worry about that. Okay.
Yes.
I'll talk to you later. Yeah.
So, sir,
okay.
Thanks a lot, sir. And nice to see you after a long time.
Yes, sure. It's a pleasure. Yeah.
It's always a pleasure to listen to your talk, sir.
Yeah. I am a CSIR man. Although I am with MHRD, I am really a CSIR person. Okay, good.
Sir, even I can remember when I was in NCL doing PhD, you taught us electrochemistry in our coursework. Oh. Then, yeah.
Yeah. Who yes, was your advisor?
Sir, Dr. Srinivas.
Srinivas. Okay. Catalysis. Yeah, Dr. Srinivas. I know. See, even we have, I don't know which year. Ashwini is here in ISA Tirupati. You might know. From NCL,
I know. Yeah, he's contemporary.
You know him.
Yeah,
Balaraman is here. So we have a mini NCL here, mini NCL. Ganesh, me, all are there. Yes. Okay.
Okay, thank you, sir. Thanks a lot.
Wonderful to have you. And I'll just click this red button, right?
Yeah. Sure, sir. Yeah.
Thank you.
Okay, thanks.
Bye.